Welcome to this lecture on Chapter 8 of the lecture notes from MM432. I'm going to cover the second part of the chapter. That is, we start with an overall introduction or review, I should say, of how to calculate U-value for a multi-layer surface. And we're now going to use this in order to study how heat exchangers can be modeled. Okay. So what I will do is I'll start sharing my screen. I'll show you where to get the key documents in order to support this lecture. So let's share. I'll refer you to the MM432 loop site and ask you to go to the lecture notes tile. And you scroll down to the very bottom and you'll see that I've added one set of overheads. So you should open these. And instead of using the web interface, I'm going to open up the PDF. Okay, so this is the document I was referring to. You'll see that I don't actually cover the overview part where I looked at the U-value, but go straight into the part of the lecture notes which starts with the parallel flow heat exchangers. So I'll open up the lecture notes as well to make sure that it's clear what I'm referring to. If you skip the first part, which is about well, the general description of what a heat exchanger is, which we've already covered, then how to calculate the U-value for a multi-layer surface, taking into account various factors, you get to a section which is called heat exchanger analysis, the log mean temperature difference. And that's the part that I want to describe now or discuss now. So if you go to the second slide of the overheads, you have this formula that's given to you, which essentially tells you how to calculate the rate of heat transfer affected by a heat exchanger. U, we've discussed what it is. A is the area of the surface available for heat transfer from one fluid stream to the other. And delta T log mean is a temperature difference, which is representative of the temperature difference that drives heat flow from one fluid stream to the other. By representative, I mean it's an average one that correctly captures the overall effect. So how do we define that average, or let's call it log mean temperature? There is a formula where you see that it's based on a driving temperature difference, that is temperature difference between the two fluid streams at one location and at another location. The actual definition of these two delta T depends on the type of parallel flow heat exchanger that we're working with or other heat exchanger. So I need to look at specifics in order to fully define this particular term. What we see also, or what you should remember, is that we did see this definition appearing previously. So for example, if you pull out the lecture notes on chapter 6, you will see that or on page 15, I should say, we had a formula for the convective heat transfer rate going from an outer fluid to the fluid inside a pipe, taking into account the possibility of resistance due to a finite thickness wall. But essentially, it was very much the same formula. That is, we had an area, we had a U-value, and we had a mean temperature difference. And that came from the fact that essentially we have a temperature which may be uniform outside, but that varies inside the pipe. Simply, there's a heat transfer to the fluid in the pipe or from the fluid in the pipe, and that means that the temperature of the fluid in the pipe will change. It means we don't have a single temperature difference driving heat transfer, but one that is varying. Therefore, we need some measure of the averaging. Another one was, and perhaps an example that's worth looking at right now, was the case of heat transfer inside a pipe to a fluid, where we had one thermal condition, which was, let's draw it out. We'll take black for the walls. So we had this type of fluid. If you have a uniform wall temperature condition and the fluid stream coming in with a certain mean temperature at the inlet and a mass flow rate, may have certain properties, but you know that if you do have heat transfer to the fluid inside or away from the fluid inside to the wall, then you will have a temperature on the outlet, the mean temperature of the outlet, which will be different from the mean temperature at the inlet. Okay, so this kind of case is reasonably simple. We have two formulas that we have to be that we can use. The first one is the rate of heat transfer by convection. It's equal to, in that case, H value, if the average one, multiplied by the area of the surface at the interface between the solid and the fluid, so the area of the pipe if it's a pipe flow, multiplied by a temperature difference. So instead of a bracket, what I should highlight here is the fact that uniform wall temperature doesn't mean a constant temperature difference between the wall and the fluid, since the fluid here changes in value. So we did need some form of averaging, and we defined that temperature difference as the log mean temperature difference. So that's to represent the convective heat transfer from the wall to the fluid. Then at the same time, we had a separate equation which told us how much heat is absorbed. Okay, absorbed, we mean that it's positive if it's absorbed by the fluid inside the pipe, and negative if it's actually released by the fluid inside the pipe to heat up the wall of the pipe. So we define that QUPS so that it's positive when you have an increase in temperature. So that would mean TMI is greater than TMO. So we would write this in this way: MCP, the specific heat capacity at constant pressure, multiplied by TMI minus TMO. So in that case, it's absorbed by the fluid because the fluids, sorry, I've got the other way wrong, TMO minus TMI, because TMO is greater than TMI, and that condition is met on the condition that the temperature of your wall, TS, is greater than TM at any point, essentially. Well, we have a heating problem, so TS is going to be greater than TM as it flows through, and that's a heating process. Okay, so that was the uniform wall temperature condition. If you had a uniform wall flux, the problem was trivial, because that means that Q dash dash is a constant or uniform over the wall, and it means that you can calculate the convective heat transfer as Q dash dash multiplied by A. So that first equation is very simple. The second equation doesn't change, essentially. Okay, all you're looking at is by how much does the temperature, the mean temperature of the fluid, increase or decrease as it goes through the heat exchanger. So this is a simple case of a pipe flow. If you modify it slightly so that you're looking at this case where instead of being given the temperature on the surface of the pipe at the area or over the surface which is in contact with the inner flow, if you're given the temperature on the outside and you assume that the temperature of that cooling fluid or heating fluid on the outside is uniform, then you can use the exact same formula, except instead of using the convection coefficient to characterize heat transfer at the surface on the inside, you use the total UA value, which represents convection on the outside, conduction through the wall, and convection on the inside. Okay, so the two problems are very similar. And now we're moving on to a slightly more complex problem, which is that of a parallel flow heat exchanger, which is the type of heat exchanger we're going to use in this lecture in order to illustrate the derivation of that formula here. Okay, so the formula is quite simple, or quite similar to the previous case, the one we just looked at, except we have a geometry which is a little bit different. So let's draw this case. We've got our heat exchanger, which I'm going to, I don't know what happened there. Okay, so the wall. I think I'm having a problem there, so I'll just resolve that very quickly. Let's draw the line again. A bit further in. Okay. The wall. And the other wall. So what do we have are two fluid streams here. So let's draw the hot stream, because I'm going to follow the color coding here. The hot stream is the one that's going to lose temperature. and we're going to say that that hot stream is coming in at a temperature TH for H for hot on the inlet, and it's going to exit with TH on the outlet, okay, with a certain mass flow rate for the hot stream. The cold stream is going to come in with a temperature of the cold stream at the inlet and a mass flow rate of the cold stream, and exits with a cold stream temperature, if you have heat exchange, which will be different on the outlet. So O stands for outlet and I stands for inlet. So we have a parallel flow heat exchanger. If you think of this as being a two-dimensional cross-section and you extrude it over a depth of, let's say, D, then you'll have a three-dimensional heat exchanger, and the surface which divides the two streams, which is shown here, is essentially the surface at the interface through which heat is being exchanged. And that surface is used to essentially separate the two fluids. You don't want them to mix. So we have a fairly simple and easy to study heat exchanger problem. This is called a parallel flow because the two flow streams are parallel to each other, and it is also called a concurrent flow heat exchanger because they both flow, or the current is in the same direction. Okay. For this type of problem, we know we have heat being lost by the hot stream, being absorbed by the cold stream, and we have a heat transfer from the hot to the cold, that is from the high temperature to the low temperature. So we can use the gray to represent the heat transfer. Okay, so that Q, I could have used black, but different color. Anyway, Q represents the convective heat transfer. Okay. Right, so let's move on to the next slide to look at that description. We have it more or less in the same way here, but I'm going to continue deriving using this document on the left-hand side. So what's the difference? We represent the thermodynamic states here on the left-hand side only with the temperature, but on the right-hand side, we also add a letter I, which refers to specific enthalpy, that is the enthalpy per unit mass of our fluid at the inlet and the outlet for both the hot and the cold stream. Why do we work with that? Simply because if you go back to the energy conservation for an open system, you should remember that in second year, it led to an equation that involved changes in specific enthalpy. But for the specific case of an incompressible fluid, such as water or liquid or gas at low Mach number, then this equality here, or these two equations here, are equivalent to the two equations here, where we've added one thermodynamic property, which is the specific heat capacity at constant pressure for the cold and the hot fluids, multiplied by difference in temperature. So the change in temperature of the hot stream and of the cold stream. So if you take Cp times temperature difference, it's the same as the difference in specific enthalpy for that incompressible fluid. It's a lot easier to think in terms of the temperature than the enthalpy. So that is why we're working with these equations here. What you need is a measure of the heat capacity. And then if you're thinking in practical sense, you need a measure of the temperature, and that's achieved by putting temperature sensors. That fairly easily easily available technology. So no challenge here. There is an alternative notation which involves the capital C there. Capital C is the heat capacity rate, which is essentially the mass flow rate, that is the amount of mass of fluid that you force through the heat exchanger on one side, multiplied by the specific heat capacity. So these two terms here multiplied together defines what we call the heat capacity rate. It's in the lecture notes, so you can have a look at that, but that's the meaning of that capital C. This is not a capital C letter. So this formula here, in the same way as we were representing early on, the rate of heat absorbed in the fluid refers to the rate of heat absorbed for the cold stream and lost for the hot stream. Okay, so one stream is releasing a certain amount of heat, that is thermal energy per unit second, and the other stream we assume is absorbing all that lost heat. So there is no loss anywhere else. Everything goes from one stream to the other, and that makes our derivations a little bit easier. Okay, so that's one assumption that you have to make in order to solve this particular problem. So that's kind of clear, or should be. The next step is to account for the other mode of heat transfer. I see that the Q here has disappeared. Okay, the rate of heat transfer by convection from one stream to the other happens at that interface. In order to be able to calculate that, you need the UA value, or the U value that represents that multi-layer surface. If you just have a convection and convection with no wall there, we assume it's an infinitely thin wall, then you can have that fairly easily using just the two convection heat transfer coefficient on one side and the other. If you want to account for conduction, you can do that, and that's what we studied in the previous video recording. Okay. The other thing is that the temperature difference that drives heat transfer is the temperature of the hot stream at a given position minus the temperature of the cold stream at another position. As you move downstream, the temperature difference changes. So you don't have a single temperature difference driving the heat transfer. And that is why we have to have some form of a mean temperature difference. And that's called the log mean temperature difference. It's defined here in terms of the temperature difference here and the temperature difference here. 1 refers to the condition at the inlet, and 2 refers to the condition at the outlet. Okay, so that's all presented here. What we'll need to do is derive all that. So I just want to make it clear here what all these terminology refer to. We've got the delta T1 are the conditions at the entrance, surface 1, and delta T2 are the conditions on the outlet at surface 2. Okay. What you have to remember is delta T refers to temperature difference that drives heat flow from one stream to the other. So it's fairly clear, TH minus TC for the driving heat transfer at the inlet, and then the same at the outlet. Once you sub that in the formula that we saw early on, we get the definition of the log mean temperature difference. But what I want to see is how did we get to that? The process is outlined here, but I'll go through it on the left-hand side. And actually, I'll expand the, well, I'll keep the two side by side for the moment. So we've got 3 forms of heat transfer, and that's always the way I think to think about it. So that would be my recommendation. So let's draw it, but not necessarily for the full system. That is, this equation here relates to the heat transfer over the whole length of the heat exchanger. But let's consider a small control volume, as is done here. So we're going to draw that control volume here. We've got a control volume on the hot side. Okay, so we have it here. And a control volume on the lower side, just right here. Okay. So we've got heat transferring from one to the other, from the hot to the cold. And at the same time, we've got heat being lost by the flowing fluid. The arrows should be the same length here. They just represent the direction of flow. But we have temperature on the left-hand side going into that control volume, which will write TH. If it comes in with a certain temperature, TH, it will have a different temperature when it comes out, provided that there's heat transfer taking place. X, we say, is this direction here. Okay. So this quantity here means the rate of change of temperature of the hot stream with respect to X, and we've moved by an amount delta X, where delta X is the, actually let's use a black color. That delta X is the actual finite width of our control volume. So as you move in the X direction by an amount delta X, you change the temperature of the hot stream by an amount, which is the rate of change of TH with X for a given delta X. You multiply by delta X, that rate of change, and you get the actual change. So you could write this, take the black, as, going all the way here, as the delta TH. That is the change in delta T. We know that the temperature of the hot stream decreases. It loses heat. The hot stream just gives away heat. Therefore, delta TH should be negative. On the cold side, we have, again, same thing, going in and going out. We've got TC, and we have the exact same formula, plus dTc over dx delta X. And this quantity here is delta TC. And in that case, this is positive, whereas this one is negative. Okay, just to reflect the direction of heat transfer. So when we go back to our definition of the rate of heat transfer, we had three formula that we said were important. First of all, we have a dq. The first one is lost. Okay, it's going to be equal, and by the way, we'll want positive values in every case, because what we want to do is actually equate them together. So I want the positive rate of heat transfer lost by the hot stream. And one way to write it, I'm going to use the capacity rate, capital C, like this one. Okay, so this one would be capital C, H for the hot. And that relates to the hot stream, release the hot stream that's releasing heat. And we're going to say, I should have used the same letter as here. So perhaps I'll edit that text and I'll put a delta here and delta, okay? Or no, I'll use a D. So let's correct here the delta, and I just put a D. So the actual increase in these, okay? Just to make sure I'm consistent with my notations. Okay, so we have, I want a positive quantity, so I put TH minus TH plus DTH over dx multiplied by delta x. And here we are. So what I'm doing is I'm using the capital, or the capacity rate multiplied by the temperature here, minus the temperature here, which is all this. And I do that because I know TH is greater than all this. Therefore, this subtraction is positive, and that's equal to CH. Actually, let me put the minus sign there. Minus CH, and then we have our DT H over dx. Okay, so that's this quantity there, which is all this quantity. The minus comes from the fact that this and this cancel out. I'm just left with minus of all this. Then we have the rate of energy absorbed. So we have C cold, and that relates to the cold one. And now I want the positive difference. I know this quantity will be greater than this one. And I forgot to change the color. So let me just, you probably don't have the color scheme yourself. Just want to stick to it. So here we have our dq absorbed is equal to CC, T cold plus dt over dx delta x minus T cold. Okay, so I take all this minus this. I don't need to put the brackets here because I don't have a minus in front, so I just leave it as is. That's going to be simply TC dTC, and I forgot the C here, over dx. Oh, no, not over dx, apologies. Being distracted. So my C here stands for cold, is a bit low, so I'm going to move it again. And C, okay. And I made the same mistake up here, so apologies for that. All I meant here is this quantity here is just dTH, so I should have had divided by dx. Okay, you could think of these two as canceling out. So that's two of the mode of heat transfer. Part is lost, part is absorbed, and then the final one is the transfer. And I'm going to follow the same convention and put a D in front, okay, meaning a small amount. The D here comes from the derivative or the differentials, and it means a small amount being transferred over a small control volume. So the dq conv, in that case, we're going to assume that that surface is small enough for the temperature difference driving heat transfer to be assumed uniform. And that's the key assumption there. We have, therefore, a heat transfer that's taking place, which is U dA multiplied by delta T. So what are the constants here? This is assumed constant, and this is assumed constant. Okay, you could make your control volumes as constant as well, of constant dA. So we could say this is, but for the moment, what we're saying is that for this particular position of those control volume, we assume delta T to be uniform or constant over the area, and U also. Now, the important part is the fact that each one of these should be equal. They're all positive. Okay, so this is positive. The minus sign makes it positive because dTH was negative. These two are positive, and these are positive. So this is the driving temperature difference from there to there, and should be considered as the positive driving temperature difference. Okay, so delta T is the positive value. So how do you make it positive? Let's go back to this. You take the hot stream minus the cold stream. Okay, but that's the basis for our derivation. So the next step is this one there, this equation. Okay, we differentiate delta T. It's a mathematical thing we'll do there in that case. So I'm going to stick with the black writing now. We start with d of delta T. We mean the differential of the driving temperature difference is going to be equal to dH minus dC, and that's the same as d of TH minus d of T cold. Okay, the derivative or the differential of the hot temperature and the differential of the cold temperature. So how does the hot temperature change as you move along the line, and how does the cold temperature change as you move along the line or the interface between the two? That's just a mathematical equivalence. Okay, we use the definition of delta T and we apply the differential operator to it, the mathematical operator. But what's interesting is that we do have a definition for delta T here, and we have a definition for dTH and dTC on the left-hand side. Okay, so we could simply substitute, and that's what I'm going to do on the next page now. I'm going to copy this as a starting point on the next page. I'd forgotten, or perhaps it just didn't translate. Okay, so we have on the right-hand side, we know what TH is. We have it here, dTH, I should say. Okay, so it's dQ. And the one thing perhaps to have written here, which I didn't at the time, is to call simply these three. So what's happening there? These three Qs are the same. Let's just call them dQ. Okay, so we're going to just simply recognize that dTH is dQ divided by minus CH. dTC is dQ divided by plus CC. So that's the same as CH plus or minus, sorry, just incorrect manipulation, minus TC it's not working, so check here. Let's go back. Minus, so dTC would be dQ over CC. So we have a fairly simple formula from where to start.